Okay, physical science time. The objective today, as you can see, we're talking now about linear motion. So the objective is arrange, Brinley, would you shut that door, please? Arrange equations for linear motion. We're talking about linear motion. What does the phrase arrange equations mean to you? What might we be doing? Very basically. Making. What very broad thing might we be doing with linear motion? Math. We're going to do some math. This is going to be largely about math. Because you hopefully will remember, that around this time last year, we talked about this conceptually in 8th grade science. Do you remember talking about motion in 8th grade science? Well, I do, and that sucks for you. We did talk about motion in 8th grade science. We talked about, do you know the word velocity? Yeah. Do you know the word speed?
Yeah.
What about acceleration?
Yeah.
What causes acceleration? Do you remember? What causes an acceleration?
Push.
Okay, we have a better science word for that. Wes?
It was where a force that is greater.
Yeah. What do we call it? There's a special word you're getting at. And I know exactly what you mean, and you're right. It's not called a force that's greater than, it has to be greater than maybe another counterbalancing force, and we call that it's not called Newton's law, it's called an unbalanced force. Caused by an unbalanced force. Caused by an unbalanced force. I hope you remember these. Do you remember, above this I'm going to write distance? You remember distance? I didn't write it first because that's pretty basic. I hope you remember distance. And do you remember displacement? These are all things to do with linear motion. I hope, even if you don't remember these from 8th grade science, which I hope you do, I think you should, especially now that I've said them, I hope you do remember these from 8th grade science, but I hope that even if you don't remember them from 8th grade science, you remember them from something much more recent, which is your vocab. These are all vocab words. Do you remember these as vocab words?
Yeah.
Let's define these things then, if you're so smart. Linear motion, let's start with that. Linear motion is, what's motion? A way of describing movement. Yeah, a way of describing movement. What was your motion in your lab yesterday? Running, maybe. Cartwheels. Somersaulting directly into a tree every single time, even though you started out not pointing at that. Those were all kinds of movement. We called them locomotion, but they're all kinds of movement. And they were motion. They were supposed to be movement in a, what's the root word of this guy? Line. Movement in a line. Now listen, can things move in ways other than in a line?
Yes.
Of course they can. But it's easier if we talk about movement in a line first and then describe the specific cases of circular or curved motion later. So movement in a line is what we're talking about today. In order to describe movement, I need to talk about three things. So in order to describe movement, I need to talk about three things, and they are direction, distance, and a reference point. Do you remember a reference point?
Yeah.
You remember what a reference point is? It's a thing to which you are referring. If I say, I use this example a lot. I'm just going to keep using it. It's kind of my thing. If I'm saying that your mom drove 70 miles an hour to Walmart, what is the direction?
To Walmart.
Towards Walmart. I have a speed which describes distance. We remember from your equation just now that distance and speed are related. Yeah, towards Walmart is the direction. The distance is described by how fast she's going and how long it takes for her to get there. And then what's the reference point though?
Walmart.
Compared to what? Like that's what reference point means. Probably not.
Your mom's car.
No. Is she moving 70 miles an hour compared to her car? No. In what case? Now that we talk about your mom, this makes it kind of sad. But talking about just any human being, in what case might they be moving 70 miles per hour relative to their own car? Only in a car crash. Only when the thing is smooshed and now your body is moving 70 miles per hour but your car is stopped. That's when people that's not a good situation. But that's the reference point generally. If we don't say one, usually we don't say relative to the flagpole at the Crawford football field, I am moving 70 miles per hour on the highway. We don't normally say that, although we are usually referring to something. The classic way to describe this is, how fast are you moving right now? Yeah, okay. You're right, Lucas. 0, you said, which you don't need a unit on the number 0 ever. 0 is not really even a number, but you don't need you're moving 0, you said, and you said thousands of miles per hour. Which one is right? Both. How? In what context? In what frame of reference? According to what reference point is Lucas right? Relative to what? Earth. Relative to the table. Relative to your buddy. Relative to the flagpole. You're moving 0. But in what context, in what frame of reference is Miranda right?
Space.
Compared to maybe the sun. Compared to the center of Earth. Compared to the center of the galaxy, you're moving thousands and thousands of miles per hour. So all of those things depend on the reference point. It depends on what you're comparing it to. When you're sitting in the car, this is not how you sit in a car. You sit like this because you can't drive. But when you're sitting in a car, really, to you it seems like, I know you've been trained from a young age that this is not the truth, and so you don't think about it this way, but to you it seems like you're still, and the cows and the fence posts and the clouds are moving by at 70 miles per hour. That's what it feels like in your brain. So compared to your car, those things are all moving 70 miles per hour. It depends on the reference point. We describe motion in these ways. Let's talk about distance and displacement now. You have questions about reference point? Every description of movement contains a reference point. If it doesn't say one, if I just say your mom's going 70 miles an hour, what's the implied reference point on this planet? Yeah, the surface of the ground. The surface of planet Earth is the implied reference point. What's distance?
Far.
Yeah, how far something is away. What then is displacement?
Displacement. When you don't place it in the right spot.
Haha, that's misplacement. Distance is how far traveled, and displacement is how far from the starting point. An example of that is if I, here's my little map. This is the school. This is Dollar General. This is me yesterday. I went to Dollar General from the school. I went like this. That's how I got there. I went in a squiggly path to Dollar General. How far did I go? What on this little basic representation describes how far I went? You can't use numbers, so there aren't numbers. The length of the line. Like if we uncurled this line and spread it all out, that's how far, that's the distance I traveled. My odometer on my car measures how far I went. I don't know, 1.5 miles maybe. But what is my displacement? How far am I from where I started? The same exact distance? No. This is kind of what we call as the crow flies. And that's what we describe with S, which is displacement. How far away you are. So maybe I traveled 1.5 miles in my car. That was my distance. But I'm actually only 1 mile away from where I started. Is there a disparity there? Is there something wrong with that? No, they're two different things. Distance and displacement are two different things. So D we use for distance. That's how far you've gone. And S we use for displacement. What about this one? Who wants to be in the example? Here's Lucas. He has a balloon because he's a little boy. And he has one of those little boy hats on. Lucas goes with his balloon and a football. He's also a football player. He goes with the balloon and the football to the end zone. And then he goes back again. Let's say he started in one end zone of the football field. And let's say we're playing 11-man football. How far did he travel in this path? 200 yards. He went 100 yards there and 100 yards back. So what distance did he travel? 200 yards. What was his displacement?
100 yards.
Where did he start?
There.
Where did he end?
There.
Oh,
0. His displacement was 0. Questions about that? You see how these things are different? They are similar. They're both measured in what unit? In the SI. There's all kinds of units, but in the SI we use meters. They're both measured in meters, but there's a conceptual difference between them.
So if you start and end at the same point, you
Yep. And is 0 meters? Not necessarily. 0 is 0 is 0. It's 0 meters, it's 0 inches, it's 0 centimeters, it's 0 microns, it's 0. Let's talk, I probably should switch these two around. Let's talk now about speed then. So speed, which we represent with the lowercase letter v, equals distance divided by time. This is our first equation that it says our objective was to arrange equations for linear motion. Our first equation for linear motion is v equals d over t. Speed equals distance divided by time. Hey, what should you do with this, do you think?
Put it in your lab.
Put it in your
Notebook.
another place too. Those are all true.
Brain.
Brain. You have to have this memorized for your test, which is Thursday. V equals d over t. Where v, without a line over it, is speed. D is distance traveled. And lowercase t is always time. What do we measure time in the SI? What's the base unit of time in the SI? Seconds. What's the base unit of distance in the SI? Meters. So then if speed, as I asked you before we started this discussion, if speed is distance divided by time, the speed unit should be a distance unit divided by a time unit. Meters per second. That's the speed unit. That's the speed unit in the SI. Are there other speed units? What kind of unit is this? Do you remember from unit conversions? We called these where a unit is divided by another unit. You remember? A rate. A time when a unit is divided by another unit is called a rate. And this is a rate. This is the rate, the time it takes to go a certain distance. That's what speed is. If I go farther in the same length of time, I'm going faster. If it takes me less time to go the same distance, I'm going faster. You saw that in your lab yesterday, right? The running, hopefully, was faster than the army crawling or somersaulting or whatever. You covered the same distance, 10 meters, in a smaller amount of time when you were running. That means you're going faster. See, looking at this equation, bigger number on the bottom means this is going to be smaller. Smaller number on the bottom is going to mean this is bigger. So less time for the same distance or a longer distance in the same amount of time would be faster, more speed. Velocity, though, velocity is distance. You remember what the other part of velocity is from last year? Distance and, or in a specific, I'm sorry, not distance. It is speed. Velocity is speed and, or speed in a certain, no, direction. It has to have a certain direction. I hope you do remember that from last year. You just forgot that you remembered it. Velocity is speed and direction. Velocity is speed in a specific direction. Let's see the equation then for velocity. I hope you can still see this on camera. If I do it over here, I think you can. V with a line over it, or V with an arrow over it, I prefer the arrow, equals S over t. You can still use d over t. It still is a distance divided by time. But since displacement is how far we are from where we started in a certain direction, remember, displacement depends on direction. This is a way to describe that. So where v with a line over it is velocity, S is displacement, and lowercase t again, you still can see this on the screen, so is time. Again, time is measured in seconds. Displacement, like we said before, is measured in meters. What should we measure velocity in then? Speed, yeah, it has to be in a certain direction. We have to indicate direction, but the unit for it is still meters per second. It's still meters per second. We just have to indicate a specific direction. So your mom going to Walmart again. 70 miles per hour could be her speed. 70 miles per hour east, because that's the direction Walmart is, would be that has a direction, so it's a speed, 70 miles per hour, with a direction, so it's a velocity. The physics book that I teach out of in physics asks the question, why do highways have a speed limit and not a velocity limit?
Because that's boring. That's velocity
Because you don't have
has a direction. You can go both directions.
Yeah, exactly. On a two-way highway, you can go both directions. So kind of, in a way, the one-way streets in Chadron there's a velocity limit, 25 miles per hour, but you can only go south. That's a velocity limit. Normal highways, I guess the interstate, you could say the interstate does have a velocity limit. You'd be in big trouble if you went the wrong way on an interstate. You'd be either dead or in prison or in the hospital if you went the wrong way. There is a velocity limit, I guess, on the interstate.
I know somebody that did that.
We don't have time on video to solve some of these. We'll do most of that practice work after class or tomorrow when you have work time. But do you looking at these equations, do you see how you would be able to solve them? You remember the steps to solving an equation. Write the equation, manipulate it if you have to. You remember manipulation? Substitute, solve, check for reasonability. Do you think, does anyone feel like they couldn't do that with one? Let's just do one real quick. I'm getting worried. Let's do a velocity one. You have this all down. Does anyone not have this down? I'd like to erase it. Is anyone not done writing it? Okay, so I'm going to take that to mean everyone is done. Is that true? You're all done? Okay. Okay. So let's say, what's a good name for a cowboy to have in a problem? Clarence. Clarence has traveled 67 kilometers east, and it took him 2 hours. No, that's unreasonably fast for a horse. It took him 12 hours to do that. Okay, that might be a problem you're given. Obviously, I'm just writing down the numbers or the information that we need, but that might be a problem like you're given on your test, for instance. Clarence, the cowboy, has ridden his horse, Bucktooth, 67 kilometers east, and it took him 12 hours. What was the speed of Bucktooth? That's the question. That might be the thing you're asked. So, the first thing we need to do is what? Always, every time. Yeah, write the equation. If it's asking for velocity, which pretend that it is, because I think that's what I said, and if it isn't, pretend it is, we're going to use V equals S over T. What's S stand for? Please do not be confused with S and speed. S is displacement. How much was his displacement? He went, from where he started, he is 67 kilometers east. So, I asked myself, do I need to rearrange this equation? No, I'm trying to find velocity. Is this set up for velocity? Yeah. So do I need to rearrange it? No. So what should I do next? What's my next step? Okay, don't say either of those things. Say the right verb. Substitute. Velocity equals, what was his displacement? 67 kilometers. We remember that it's east, but we don't actually do math with the letter E for east. What was the time? 12 hours. Just to make it easier, let's pretend Clarence didn't quite make it there and he only went 60 kilometers, so I think I can do that math a little bit more easily in my head. 60 kilometers, he gave up almost all the way through. Okay, velocity then equals, for our solution, 60 divided by 12 is 5, but we're not done because kilometers divided by hour is kilometers per hour east, because he was going east. 5 kilometers per hour east. Now, your problem might also say, instead of just saying his velocity, it might say, what was his velocity in meters per second? And if that's the case, then we have another step. And what's the other step? Conversion. You can do this two ways. If it asks you to use a different unit than you actually got, you can either convert both of these to the units you'll need at the end, at the beginning. That was a little bit confusing. You can either, at the beginning, convert each of these to the units you'll need, or at the end, convert the answer to the unit you need. Let's do that second one. So 5 kilometers over hour, going from kilometers to meters, going from hours to seconds. Make sure you show all your work on this, which includes all of these conversion bars. 3,600 seconds in an hour, 1,000 meters in a kilometer. Answer? Calculator, please, Brindley. So sometimes we need to convert either okay, I guess I'll do it myself, Brindley. I'm going to type into my calculator. I was hoping you would do this. 5 times 1,000. I don't even have to type that in. Divide by 3,600. Enter. I get 1.4 meters per second. Because look, kilometers reduced to 0. Reduced to 1. Hours reduced to 1. I'm left with meters on the top. Seconds on the bottom. 1.4 meters per second. Which is about 3.5 miles an hour. Is that reasonable?
Yes.
Yeah. A walking horse probably does move about 3.5 miles per hour, which is kind of surprising because I made this question up entirely in my brain, and so it's weird that the answer is reasonable. Questions about speed and velocity?
Yes.
Okay, what is it?
No, I meant no.
Okay, cool. The last thing we need to talk about then is acceleration. So, and you should, once again, like these other things, you should know the concepts of acceleration from last year, but acceleration is a change in speed. Remember that? Acceleration equals change in speed, change in velocity over time. Change in velocity over time. Look at this weird equation that I just wrote. Oh no. What's the triangle mean? There's a triangle here. Triangle is not even a letter. Why is a triangle in here? The triangle is a letter.
Delta.
It's delta. You remember, or you know, or what are you talking about? Delta means, and you need to write this down. I know this is on your test. In fact, I'll tell you, it is number 9 on your test. Delta means change in ... Change in whatever thing follows it. Okay, that's not how you start a triangle.
What's the upside down triangle?
This is the letter V. You remember from the alphabet. So delta H means change in height. Delta T means change in time. Delta capital T means change in temperature. They all just mean change in whatever the next thing is. So in this case, we have change in velocity. Another way to write this is not a separate equation. Another way to write this, anytime we have delta, we can replace it with the thing we're talking about sub F final minus the thing we're talking about sub naught, which is with a little zero down there, meaning initial. Once again, over time. These two things mean the same thing. Anytime you see delta, delta H equals height sub final minus height sub naught, which is final height minus initial height. When might this apply? When might something change in height?
When they're building a building.
Yeah, sure. When you're building a building, maybe one day you go by, it's 100 meters tall. The next day you went by, it's 200 meters tall. Let's do that one. Let's say the change in height was 200. So what was my final height there? 200 meters is the final. Notice the final comes first. Minus, what was my initial height? My first height? 100 meters. So what was my delta H, my change in height? 100 meters. We always put the final one first. So this equation means the same thing as this equation. They are, well, stopwatch. That's not what I wanted. I want to see how much time is left in class. Oh, we're good. We can always replace delta whatever with that thing final minus that thing initial. The change in whatever quantity is the final amount of it minus the initial amount. So when we're talking about acceleration, there are 3 ways an object can accelerate. You remember this from last year. This is a review. 3 ways an object can accelerate. What are they? Remember, acceleration is change in velocity. How can velocity change? Increase. What do we call that generally? Speeding up. Right? Speeding up. Because part of velocity is speed. 2, slowing down. Slowing down, we sometimes in lay people's speech, I mean like non-scientists, sometimes call that deceleration. Let it be known that deceleration is a kind of acceleration. In physics, acceleration is any change in velocity. We usually in our daily life say accelerate when we mean go faster, and decelerate when we mean slow down, but deceleration is not a physics term. Both of those to a physicist are acceleration. And then what's the other way? What else is velocity made of? It's speed and distance. Nope. Speed and, you tricked me. Speed and, velocity is speed and direction. So how can an object also accelerate? Change in direction. Even if, this is where everyone gets tripped up. There are about 5 questions on this test exactly like this. Even if the object is staying at a constant speed, like it's doing a little cookie in the parking lot, staying at a constant speed. Look, my arm is staying at a constant speed, but it is constantly changing direction, so it is accelerating. Okay? Change in direction. That means there are 2 ways an object is not accelerating. In what 2 cases is an object not accelerating? Stopped. That's the easy one. What's the other one then?
Staying at the same.
Yes, exactly. Great job, Lucas. No one ever gets that one. Straight line and constant speed. When, again, when your mom is driving to Walmart at 70 miles per hour with the cruise set, she's going in a straight line at a constant speed. She is not accelerating. You know what acceleration feels like. What about when your mom goes around this corner outside of Crawford? Do you feel that? Even with your eyes closed, you can tell she's going around that corner because the direction has changed. Yes, Wes? Yeah, it's because there's a force applied to it. That's exactly right. That's what we're going to talk about next. Don't forget this one, and don't forget this one. Those are the ones that people forget. Change in direction is an acceleration. And even if you're moving at a constant speed in a straight line, you are not accelerating. Acceleration is change in velocity. Acceleration is change in motion. So if your motion is not changing, That doesn't mean you have to be stopped, but if your motion is not changing, you are not accelerating. Similarly, if you are changing, even in just the direction, you are accelerating. And you can feel acceleration. Your body has built-in acceleration feelers. Your whole body feels acceleration. When you're going in a cookie, you know you're going around a cookie even with your eyes closed. Even though you're going at a constant speed, you feel acceleration because there's a change in the motion. What causes acceleration? Last thing, what causes acceleration? Yeah, no, not any force. What causes? Are there forces acting on my keyboard here? What forces are acting on my keyboard here? Okay, we'll pretend it's sitting still like it is. Yeah, so here's my, I think you can see it if I draw it over here. Here's my keyboard. What forces are acting on it? Gravity, you said? F sub g is gravity. What else? What other forces acting on it? If this were only acting on it, what would it do? What must it do if this is the only force acting on it? Fall. Yeah, it must accelerate if there's only an unbalanced force. But what force is balancing this? The stool. We call that the normal force. The force that's pushing up against gravity is called the normal force. So these forces are F sub net, the net force equals what? Well, it has this, yeah, it has, let's say 1 Newton up and 1 Newton down, so 0. But if I don't want to do it with my keyboard because I'll break it. If I do it with the marker, those ones, when they were falling, I'm going to draw a little picture here. This is the marker. Whoa! As it's falling, F sub g, there is a little bit of air resistance here. But the net force, F sub net, equals not 0. It does not equal 0. This is called an unbalanced force. What must something do if it has an unbalanced force acting on it?
Not equal 0.
Yeah, it must have a force not equal 0. It must have a net force not equal 0. And it must not just move, Lucas. It must accelerate. It must change its motion. When you walk to second hour, where's your second hour class? This is you walking. I assume this is how you walk. You are accelerating. You're going from not moving to moving. That is an acceleration. What is providing that force to you? In your case, it is the force of your muscles pushing back on the floor makes the floor push you forward. So unbalanced force causes acceleration. Does every force cause an acceleration? No, only unbalanced forces cause an acceleration. Okay, and then last thing before we go, we can graph all of this. You know about graphs? The common way to graph this is to have something on the time. I think actually time goes on the x-axis. Yeah, time goes on the x-axis. So as time goes on, these things change. Let's pretend that we are accelerating. Let's pretend you're this marker. Woo! On a acceleration time graph, what's the marker doing? As time goes by, the marker has some acceleration. There's some, we'll say it's got 1 acceleration. That's not really a unit for acceleration, but we say it has 1. So this on this graph, it's flat. What's its velocity doing? Yeah, its velocity is increasing as time goes on. What is its displacement? What is its distance from where it started doing? It's going up, but it's going up faster and faster and faster because it's accelerating. So its distance looks like this. So this curve is an acceleration curve on a displacement time graph. This velocity is increasing because that's what acceleration is. Or, remember, acceleration can also be decreasing, but in this case, the velocity is increasing because that's acceleration, and the acceleration is just staying steady. What about in the case of your mom on the highway? What's her displacement doing? It's going up, but it's not going faster and faster and faster, right? It's just increasing at a linear rate. What's her velocity doing?
It's going.
She's going at constant, yeah, staying the same, so just a flat line. What's her acceleration? Is she accelerating? No, so acceleration is 0. Do these graphs kind of make sense to you? We use these 3 graphs to describe linear motion. A curve means it's getting bigger and getting faster at how much it gets bigger. A straight line means it's getting bigger, and a flat line means it's steady, and then this is 0. Do you think you'd be able to read a graph like this? This is the whole point of like the MAPS test and the ACT and everything is reading graphs like this. Do you think you could read one like this? Okay. Do you have any questions? This was a lot of stuff. But the concepts of it, I'm hoping you remember. This was kind of ringing a bell as we went through it. I hope that what was new to you in this lesson, like actually fresh information, was these graphs and then the math we did. The equations you need to have memorized. This is the last thing before we go, and this is just a little review from what we already talked about. But the equations you need to have memorized are v equals d over t, that's speed. Velocity, v with an arrow, is s over t. Acceleration equals delta v over t. Those you have to have memorized. You must have these memorized. What's another way of writing that last one? Remember, it's acceleration equals v sub f minus v sub naught over t. What are we going to do with these equations?
Remember them.
Memorize them in our memory bank. Where'd my lid go?